Okay, so let's move to lecture 1, introduction of diffusion in solid materials. So in these sections will be divided into 4 parts. The first one, we are going to talk about the difference between the thermodynamics and kinetics. And as you know, in thermodynamics, we always talk about the equilibrium conditions or equilibrium states. But here in kinetics, we care about the time dependency, means the velocity about the kinetics process. So that means you need to calculate the rate, how this reaction or process change with time, and you also understand you need to calculate or estimate the exactly rate. Is it happen fast or slow? Then the second part we are going to talk about the equilibrium state versus the steady state. Equilibrium state actually is divided or determined by the thermodynamics. And as you know that the state function does not change with time in the equilibrium state in thermodynamics. That means what's the state function? For example, like the pressure, temperature, entropy. In the equilibrium state, this state functions does not change with time. But in kinetics, actually, we are interested in the reaction rate, right? Or the velocity, or how fast or how slow this kinetics process happen. So we are not going to talk about the steady state. Instead of that, we are talking about the steady state. So steady state, some people also call it as a steady flow process. Flow process means what? Means there's something flowing or moving through your materials or systems, right? So that's what we are interested in. So the flux here can be what? Can be, for example, like I can draw something. So the flux here can be the heat flux, heat flow, electric, so probably can. Okay, so can be the, let me draw some. So here can be the flux can be the heat flow passing through your materials, or the current density going through your materials, or the atomic flux. That means the diffusion, some atoms moving or migrate through your materials. So and some people probably will ask, yes, you have a heat flow, so as long as you had heat flow, next step you will think come out from your mind probably will be definitely something drive this heat flow, electrical current density, or the atomic flux, right? So the heat flow, the driving force definitely is a temperature gradient. And for the current density, definitely you have the electrical potential gradient be applied on your systems. And for the diffusion happens, you have a mass transport, atomic flux, definitely you have chemical potential gradient exist in your systems. So based on this, you know, if we want to well describe a kinetics process happen in your systems, or if you want to well describe what happened, what's the flow process, you have some indicator parameter, right? You can see the flux and definitely have a corresponding driving force. And in order to quantitatively describe how fast this flow process is, so we will give you a indicator which we call entropy production rate. So we can use the entropy production rate to describe how fast the flow process is. And we also can, at the third part, we can give you a beautiful equation which can link the flux and its corresponding driving force, and will be equals to the absolute temperature times the entropy production rate. This means as long as you measure or you know the flux and find out the driving force which you apply or be applied on the systems, and you know the temperature, the working temperature here, so you can simply estimate the entropy production rate for this your interesting flow process, right? So this is a very important indicator to describe how fast this flow process is. Okay, so at the end of these sections, we are going to talk about how about if our system have two or more driving forces, which will result or lead in two or more flux. How can we get the entropy production rate? Are there any coupling effect in between these two forces? For example, like if let's take an example here. If we have, maybe we need to change color. If we have, if I apply a temperature gradient and also the electrical potential on our systems, as you know, as long as I apply temperature gradient, that will lead the heat flow, right? And also because in the meantime, I also apply the electrical potential on the two ends of my materials, so that will lead the current density. Now the problem would be, does this temperature gradient contribute some electrical current? Oh, and if this electrical potential cause some increase or decrease in heat flow. So this kind of coupling effect we call this coupling effect we call it is a coupling coefficient, right? And this only happens on if we have two or more driving forces coexist in your systems, then that definitely will contribute some flux, no matter it's this one or this one, and they have definitely a coupling term. And this coupling coefficient, if you got the higher values of coupling coefficient, which means when you apply, that means in this case, that means when you apply the electrical potential, that will contribute more or larger, that will change a lot in heat flux. The same thing happen if the coupling coefficient is quite large, then that means when you apply a temperature gradient, then that will increase the current density, or increase or decrease the current density in your systems. Okay, so this is all we are going to talk about in the lecture 1. So let's move forward. So let's give you an example. Let's from the difference, talk about the difference between the thermodynamics and kinetics. Before we move to next slide, so I will give you examples to hope can well describe the difference between the thermodynamics and kinetics. Thermodynamics, you can consider some reference coordinate. Consider as a reference coordinate, and this also some people also call it as a state, certain state, or you can also call it as a reference coordinate. That's for example like now we are in Hsinchu, right? And if we want to go to Taipei, and the location in Hsinchu and the location in Taipei, you can consider as the specific state in thermodynamics. Because the location, this location of Hsinchu and Taipei does not change with time, can be considered reference coordinate. And what's the kinetics involved here? If that would be because kinetics means we are interested in the velocity and rate, right? So if I want to go to Taipei, from Hsinchu to Taipei, so what kind of transportation I'm going to take? That would be the kinetics process that involve the kinetics. Because first of all, because I want to go to Taipei, so I need to choose yes, I can choose the transportation, and also I can choose the different path to arrive Taipei, right? So in kinetics, we care about which path you are going to choose and the corresponding rate of velocity. Okay, so I hope this can give you some idea. So in this case, we know that thermodynamics can help us to define the state of our systems. Then kinetics, as long as we know, we need to define the state first, right? Then we need to determine the start point and the end point. That means I want to know the state 1 is the start point, then we want to move to state 2. And what kind of path we are going to choose and the corresponding velocity it involves is a kinetics process. So if you use the same concept into the material system, so next slide is in material system, how can we determine the state, or how can we well describe a state of the material systems? So the parameter we are going to use can be the composition of the materials, composition in percentage. The phase means the crystallinity, or for example, like the BCC, FCC is different crystallinity, or also can be the solid, liquid and gas phase. And also you can use the pressure, temperature, charge state, and even different types of defect to describe the state of your material systems. And as you know, the thermodynamic state is a function in a multi-dimensional space, which means we definitely have some state function can be changed or varied with different materials properties, or you can say it can be changed at different conditions of your materials. So N1, N2, N3, N4 can correspond to composition, phase, pressure, and temperature. And the state function usually people use can be the energy state function or entropy state function, right? So now you know, in order to well describe a state of your material system, we usually will use a state function, and also we will input. We know that there are several different parameters which can help us to well define that state of your interesting materials. So give you an example here. So what we have is we have a lead tin by binary phase diagram, and the horizontal axis represent the composition, and this is the tin rich side, and this is lead rich side, and this is tin rich side. And the vertical axis expressed is the temperature. So in this phase diagram, you can simply identify the phase involved in doing this temperature and the composition. So now if our material system is located here, so we know actually it is in liquid phase. If in this region, now we know it will be the alpha and liquid phase. So here you can simply know alpha phase actually is a lead rich phase, and beta phase actually is a tin rich phase. And this phase diagram have a very special point which we call a leutetic point. At this leutetic point, you can observe there are 3 different phases coexist at this specific composition and temperature and also the pressure and so on. So any point here in the phase diagram actually it definitely is a equilibrium state. Okay, and this state can be expressed like you can use any state function, and you also can put any some parameters here as an example. For example, like you can put the energy state function here. For example, like a G gives free energy, and this one you can put what composition, temperature, pressure, and so on to define this state. And now if we are interested in this state, which also can be well defined by composition, temperature, and also the pressure and the phase, right? So this can be considered and be defined in thermodynamics, and also this can help you to describe a material system, right? And as we mentioned before, we can use the energy state function to well describe the material systems and process, right? Okay. Next, how many energy state function you learned before? I will say there are 4 different types of energy state function, including the internal energy, enthalpy, Ampere's energy, and Gibbs free energy. So next following slide, I'll give you a very quick review about how we get the energy state function. These 4 energy state functions, starting from the laws of thermodynamics. So as you know, this will be a review part. So as you know, the first law of thermodynamics is the energy conservation law, and this law actually describe like definitely only can be performed in a closed system. And this first law states that the energy can be converted from one form to another with the interaction of the heat, work, and the internal energy. But it cannot be created or destroyed under any conditions. So in this case, we know that as long if I am a system, so the heat observed by the system can be used or can be converted to increase the internal energy and can be used to perform some work. Okay, and this is what we call energy conservation law. And the second law is also very famous, right? The second law actually is related to the entropy. The second law establishes the concept of entropy as a physical property of the thermodynamic system. And this entropy can predict the direction of the spontaneous process, or you can say can tell us the direction of your interesting chemical reactions or your interesting process. So the entropy, the change in entropy be divided in when we have the reversible process. And the heat change at a constant temperature will lead a change in entropy. This is a definition for entropy. And as you know, if we are talking about in a reversible process, then the entropy change would be equals to 0. And so this the change in entropy can help us to predict the direction of this chemical reaction or process. That can be help us to define whether or if this reaction is irreversible or impossible. If the entropy change is larger than 0, that means definitely this reaction is a spontaneous irreversible process. But however, if the entropy change is smaller than 0, that means the entropy change is negative, then not tell you this definitely an impossible reaction. And the combination of first and second law lead to the following equations. And this actually is an energy state function. That tell you that the change of internal energy equals to T times the change in entropy minus the pressure times the change in volume. And this equation can only be used in the closed system. So now we have some idea about the change in internal energy, right? And we still have 3 more, right? So there are 3 more energy state functions, included the enthalpy H, Helmholtz energy A, and Gibbs free energy G. And this be defined as following, like the enthalpy be defined as internal energy plus PV. And the Helmholtz free energy A defined as the internal energy minus Ts. And the Gibbs free energy be defined as enthalpy minus Ts. So even though we have got the energy state function related to the internal energy, so we still want to have this others, right? So how to get this one? So I give some examples here, then you can know how we get or derive this relationship for enthalpy. So we take the deviation for this equation, so we will get the dH equals to du plus p dv and dp times v plus the dp times v is like this, right? And as you know, du here equals to TdS minus PdV. So you can delete this term and this term, and what you left is the TdS plus VdP. So we got here dH, the change in enthalpy, will be equals to TdS plus VdP. The same thing can be performed for A, Helmholtz free energy and Gibbs free energy, like this. dA equals to du minus TdS and minus dt times s is like this. And du can be replaced as TdS minus PdV. So what we have is we delete the plus and minus term, and what we left is this and this. So we successfully get the change in Helmholtz free energy equals to minus S dt minus P dV. And for the Gibbs free energy part is dg equals dH minus T ds. So here is dH minus T ds minus dTs, right? And the enthalpy, dH, can be expressed like dH is here, so you just substitute here. So you can get this term and VdP, and TdS minus plus TdS minus TdS. So you left, you just have here. So it's VdP minus SdT. So you got this one. So here we successfully get the four energy state function, including the du, dh, dA, and dg. But this energy state function can be applied in a closed system of fixed size and composition. But unfortunately, when we talk about kinetics process, no matter it's a diffusion, chemical reaction, or the phase transformation, it always involves what? The volume change. It cannot, sometimes it cannot be the closed system, and sometimes the composition changes as well. So it turns out, if I want to use this for energy state function, it's not going to work in kinetics, right? So we need to modify that in order to what? We hope we can use the energy state function to describe the phenomena or estimate any velocity rate stuff in kinetics. So definitely we need to modify these four state energy functions. So how to do that? So I'll give you, we take the Gibbs free energy as an example to tell you how can we deal with if we have some variations of composition and size of the systems. So now we take the Gibbs free energy as an example. As you know, the temperature, pressure, and composition of the atoms can well describe the state of our material system, right? And it also can change the Gibbs free energy in the meantime. So we can write down like this. And also, we can, in order to know how the change in Gibbs free energy by these different parameters, so we can write down like this. So the change in Gibbs free energy will contribute from the change in temperature, and the rest parameters are fixed, and plus the change in pressure, and the rest parameters, for example, like T and composition, are fixed, and plus the change in Ni component, and the rest of parameters were fixed, and so on, right? So now we have this relationship, and we make a assumption. If the compositions remain constant during the process, which we know that you can directly write down the dg equals to minus SdT plus VdP, right? And when you compare these two equations, so what you get is you will get like minus S minus entropy equals to this term, and partial G partial P equals to V, and the rest of part can delete that because the composition remain constant, so we don't have any changes in Ni, Nj, and Nk, and so on. So now you can rewrite this equation as this one will be minus SdT plus VdP, and we have extra term is related to composition change, so we summation them will be partial G partial Ni, and the Tp and other parameters will fix, and the Ni, and we summation I equals to 1 to k. That depends on how many atoms we have here. So in order to deal with the variation of composition and size change of our system, we get the new energy state function, Gibbs free energy state function. expressed like this. And one thing we need to emphasize will be this very famous potential we call the chemical potential of the species I is this term. So mu I actually is a chemical potential of species I. So if you take this closely, so what's the mu I chemical potential means? That means when you at the constant temperature, pressure, and the rest of composition does not change under that conditions, when I added 1 moles of I atoms in our systems, how much the Gibbs free energy increase or decrease? That means the chemical potential of the species I. Or you can so this is the definition for chemical potential mu I. So chemical potential of species I means the increase in Gibbs free energy while added 1 I atoms at constant temperature and pressure. This is we call the chemical potential of species I. So now we have a modified Gibbs free energy, right? So this modified state function, energy state function, can be applied to the open system or closed system with composition changes. So that can help us to deal with the kinetics process, right? And the same technique can be performed in the rest of 4 parts, including the DH. We just ended the chemical potential term here, or you can call it as a composition change term here. And for the Helmholtz free energy, we only end this term, Gibbs free energy, yes, and internal energy, and simply end this extra chemical potential term related to the composition change. So this we just simply list 4 energy state function. In this slide, we are going to give you a brief introduction about how to choose probably I will say what kind of energy state function we should choose for our systems. So that would depending on the constraint, or that would depending on the systems we are dealing with. So I will give you some examples step by step. So for the internal energy, du is a change in internal energy equals to the change of heat, mechanical work, and also the non-mechanical work. Here I want to mention that PDV actually is a mechanical work, right? And the composition change part, which we just derived from the previous slide, actually some people will call this term as a non-mechanical work, dW prime. But this term can also be not only for chemical potential, can also be if you have the interfacial energy, land heat, or Joule heating stuff. So you can plus all the other work here to modify this state function, energy state function. And next is the enthalpy. Enthalpy actually, I would say the mechanical engineering usually use the enthalpy or choose to monitor the enthalpy, because the mechanical engineering will deal with under the isobaric process. That means the constant pressure conditions. So you can drop this term out, and if there's no non-mechanical work, so you can drop this term out as well. So in this case, you can know the change in enthalpy or equals to the TDS and also equals to the change of the heat. And related to next one, Helmholtz free energy, which usually will be the chemical engineering will care about. They will use the change of Helmholtz free energy frequently because usually they will manipulate the temperature, right? So in the isothermal process, it means that dT equals to 0. Then when you can get the change in the Helmholtz free energy will be equals to what? The total, the mechanical work plus the non-mechanical work. That means the change in Helmholtz free energy will equals to total work applied on the system. Okay, and we are the material scientist. We always we prefer to use the Gibbs free energy. Why? Because in most of cases we deal with the solid state conditions, then that will be the isothermal and isobaric process. That means tell you that dT and dP equals to 0, and you can delete these two terms. So in this case, you know the change in Gibbs free energy will equal to what? The summation of the non-mechanical work. So you can know how much the non-mechanical work done on these systems easily by using the Gibbs free energy as an indicator. And in the, I don't know whether you remember that in the thermodynamics class, you spend lots of time to calculate the change in Gibbs free energy. And some people will ask, this energy related to kinetics or diffusion in solid materials? Any clues or anything can help us to know there's definitely some links between them. Yes, if you take a look here, dNi, what's the dNi? It's like the composition change. That means definitely have a mass transport happen in your systems. So this is a small clue tell you that there's must a diffusion or something happen in your systems. Okay, then let me give you a quick summary for the energy state function. The energy state function are changed by the work done on or by the system, and also the heat flow into or out of a system. And this state function sometimes, as long as it is kinetic process, and there's some work or heat flow happen into our systems, there's definitely accompanied with the entropy generation in your systems. And which energy state function we should choose or use will depending on different constraint. That means under different conditions. For example, that if the condition environment we deal with is a constant pressure and constant volume and no mass transport. So the constant pressure, constant volume. So let's take a look on the internal energy and enthalpy part. If it is a constant pressure, this is the delete this term, right? And constant volume, so we know the change in internal energy will equals to change in enthalpy and equals to TdS. TdS actually is the change in heat. If the same thing happens in Helmholtz free energy and Gibbs free energy, then what we get here is this term drop this term, drop this term, so this equals to this. So the change in Helmholtz free energy equals to change in Gibbs free energy and equals to minus SdT. Okay. And because there's no mass transport, so you can delete this term out, right? And the second example here will be if the case we deal with is a constant pressure and constant temperature, then in this case I will use the Gibbs free energy or monitor the Gibbs free energy, because the change of Gibbs free energy directly equals to the change in the chemical potential part due to the composition change because there's a mass transport term here. And just a quick remind, Gibbs free energy is energy term, so we also can monitor the change in Gibbs free energy to know the direction of the reactions or process. Because finally, the systems always decrease the to minimize the energy of the system. So you know that the dg definitely smaller than 0, right? Like this. Sorry. Okay. So if you draw the x is a location here. Okay, so this is the gives energy, and this will be, I would say, can be the reaction coordinate. So now we have state 1 have G here, and state 2 have G here. And the horizontal axis means the reaction coordinate. So here you can the system definitely move from 1 to 2 because this will lead the decrease of the total decrease the that will decrease the total energy of the system. And in this case, G, this one, small g minus larger g, so dg definitely smaller than 0. So if you monitor the change in Gibbs free energy, also can give you some information about the direction of reactions and process. And the last one example here will be when we have a constant volume and constant temperature. Then if you estimate the change in Helmholtz free energy, and you also can know the change in chemical potential term due to the composition change. But here, in most of cases, we don't use the Helmholtz free energy as an indicator to help us to know the reaction directions, because it's very difficult to know or confirm that the volume is fixed. In most of cases, we don't know. It's very difficult to measure whether the volume is fixed or not, right? So as a material scientist, usually we use the Gibbs free energy as a state function. Gibbs free energy, this kind of state function, as an indicator to describe, help us know the reaction directions. Okay.